crystal lattice, there is a parallelepiped constructed from vectors which correspond to translational periods called unit cells. These can be chosen in different ways. Commonly, unit cells are chosen so that their vertex coincides with one of the atoms of the crystal. Then lattice sites are occupied by atoms and of the atoms of the crystal. Thus, the lattice sites are occupied by atoms and vectors that connect the nearest equivalent atoms. The unit cell contains at least one atom of each kind that make up the crystal. Providing that the unit cell is made up of only one type of atoms, it is called monoatomic. Any more than that is known as polyatomic. Correspondingly, a monoatomic lattice is often identified as a simple lattice and a polyatomic one a composite lattice. One such example is table salt, that is NaCl. Now moving on to Bravais lattices, there are 14 types of lattices, and a Bravais lattice is a set of all equivalent systems in a crystal that are able to be brought back to themselves when they are displaced by a unit length in a direction parallel to a unit vector. Bravais lattices are not always primitive, having one point inside the unit cells. Other points can be found outside the unit cells. These lattices are classified according to symmetry and space rotations into several crystal systems. Now, what is exactly a 7-crystal system? A 7-crystal system is a system in which a group of crystals are organized according to their axial systems and the angles which they make with the coordinate axis to make the classification of crystal easier. The first one of them is cubic. Now you can visualize this cutout as a cubic crystal because it doesn't have equal faces. If it had one, so it would have been a perfect example of a cubic crystal system. The cubic crystal system is also known as an isometric system. It is characterized by its complete symmetry. The system consists of crystallographic axes which are perpendicular to each other and as well as equal in length, and these are all inclined at an angle of 90 degrees to each other. Now moving on to the next system, that is hexagonal. The hexagonal crystal system consists of crystallographic axes that are inclined to each other at an angle of 120 degrees, and the fourth axis is perpendicular to that plane. These might not be equal in length, and it is different from a cubic system in the way that you can see the unit cell here is not cubic in nature, it is hexagonal in nature. Now my friend will continue on with the next crystal systems. Thank you.
My friend left off. Tetragonal crystal lattice. A tetragonal crystal is a simple cubic shape that is extended along its vertical as well as horizontal axis, creating a rectangular prism. It consists of a square base and a top, as well as 3 axes. These axes are one perpendicular and two horizontal with 90 degrees. Like the cubic system, it is composed of 6 faces. Moving on to the next one, rhombohedral crystal system. A rhombohedral is a triagonal system that has 3-dimensional shape similar to a cube, but it has been inclined at an oblique angle. It consists of 3 axes, one vertical and 2 horizontal, all laid perpendicular to one another. These axes are 90 degrees to each other. The rhombohedral is composed of 6 rhombic faces. It is similar to this shape. You can visualize it. Instead of the rectangular faces, it has rhombic faces. Moving on to the next one, orthorhombic. Orthorhombic crystal system consists of 3 axes. These axes are mutually perpendicular, all having different lengths. Yet the axis angles are equidistant, laying 90 degrees to each other. The orthorhombic also has 6 faces. Monoclinic. A monoclinic has all unequal axes. The vertical and forward-facing axes are inclined towards each other at an oblique angle, and the horizontal axis is perpendicular to one another and is known as the orthoaxis. These angles are all arranged in 90 degrees to each other. A monoclinic system is also made up of 6 faces.
So guys, I'm just gonna summarize what the other 2 people said. So basically, space lattice is an arrangement of points with each point having exactly same surroundings. Consider this unit cell, and it is repeating in every direction you see here, like from below, from everywhere, making a big lattice which is called a space lattice. Symmetry operations restore a body to its original position. And there are 4 kinds of symmetry operations. One's translation, one's reflection, one's rotation, and another one is inversion. And there are 32 point groups and 230 space groups. However, Magnan's symbols are used to denote point groups. So now we move on to Miller indices. Planes in a crystal are described by a notation called Miller indices. Miller indices of a plane, indicated by H, K, and L, are given by reciprocals of the intercepts of the plane on the three given axes. As you can see, this y-axis, x-axis, and this z-axis. The plane which intersects x-axis, basically this axis at 1, has one lattice parameter and is parallel to y-axis. As you can see, is parallel to y-axis and even z-axis, as you can see here. So Miller indices has H as 1 by 1, K as 1 by infinity, that's 0, and I is equal to 1 by infinity, that's again 0. So basically HK is written as, which is equal to 1, 0, 0.
Consider this structure as a body-centered cubic structure. So here you can see that this point, it is a body-centered atom which is lying at the center, and consider these four as the vertices of a cube. So in a body-centered cubic structure, there are 8 atoms on each vertex, like 1 atom on each vertex. So their contribution to the atom is 1, but then according to this atom contributes as a whole. So the contribution of as a whole structure, it's 2. So according to our atomic packing fraction formula, we calculate the fraction as 0.68, or the atomic fraction can be calculated as 68%.
Consider this face as a face of a simple cubic structure with each of the two hands representing a side of a cube. Since our atom is a sphere, so the volume of the sphere is 4 by 3 pi a cube, and which I am telling that this r and this r, that means 2r is equal to a. That means 4 by 3 pi a cube, and the side of the unit cell is a cube. So from the formula of the atomic packing fraction, we can say that volume of the atomic unit cell into the number of atoms by volume of unit cell. From the relation of atomic packing factor, r is equal to 0.5a, and we are going to substitute that formula in the atomic packing fraction, in the formula of atomic packing fraction. So by this we come to that conclusion that the atomic packing fraction is 0.52 and the packing fraction percentage is 52%. Thank you.
Now coming to the calculations, we need to explain how the diagonal comes to be r is equal to root 3a. So first we consider one face of the cube. Here, as you can see that this face, consider this one face. So this is the diagonal and these are the 4 points. So according to Pythagoras theorem, we calculate the radius from here as r is equal to root 2a. Now when it comes to the whole cube, there is a body centered atom which is located at the center. So imagine a diagonal crossing the whole diagonal of the cube, and the diagonal as we calculated is root 2a, and consider one side as a. So according to the Pythagoras theorem, then we get the resultant radius as root 2a whole square plus a square is equal to 3a square. So we get the resultant r as root 3a. Thank you.
Hi everyone. So let us consider this formation as a face-centered cubic structure. So the guy sitting behind these faces as considered as a center of each face. So each face contributes half to the unit cell, and so the number of atoms contributing here would be 4. So now let us consider this face. When we consider this face and we consider a side to be A and this side to be A, so when we by the Pythagoras theorem we get this as root 2a. So by that we get the relation as r equal to a by 2 root 2. With that, we according to the atomic packing fraction, we get that the number of packing fractions would be 0.74 and the atomic packing fraction would be 74%. Thank you.
Isn't the best way in summer, how electrons come and go. The empty states of matter feel the fall in the place in the black hole. Sorting apart
and suddenly say yes. Electrons move too much. Slow down your pace and put that on your knees. Coming now, follow my lead. Coming now, follow my lead. Orbitals take the shape daily. Stable states of the quantum. And one approaches. They command their bonding. Thus hydrogen as the root is found in its truth. Automatically bonding. Oh high, oh high, oh high, oh high. Automatically bonding. Oh high, oh high, oh high, oh high. Automatically bonding. Oh high, oh high, oh high, oh high. Automatically bonding. Energy configuring bonding. When all stay the same day.
Let us learn how crystals are formed. Crystals are formed by a process called crystallization. Crystallization is a process for the formation of solid crystals from a uniform solution. Crystallization is also a chemical solid-liquid separation technique in which mass transfer of a solute occurs from a liquid solution to solid solution.
During crystallization, tiny crystalline structures called nuclei are formed. This process of nuclei formation is called nucleation. Now, there are two types of nucleation. One is homogeneous nucleation and heterogeneous nucleation. What is the difference between the two? Assuming these are tiny nuclei, we see that in the lower half of the beaker in our illustration, the nuclei are formed in an orderly manner in subsequent layers. However, at the top, the nuclei are formed in a haphazard manner. When the nuclei are formed in an orderly manner, it is known as homogeneous nucleation. And when the crystals are formed in a haphazard manner, it is known as heterogeneous nucleation. Hi, I'm Vaden Norona and now we are going to talk about conduction of electricity in crystals. Now we will learn how crystals conduct electricity due to the motion of ions. This method wherein crystals conduct electricity due to the motion of ions is called ion hopping. In our illustration, let us assume that this is a crystal lattice, wherein the big spots are anions while the smaller ones are cations. When an ion hops, it either moves into a vacant site or an interstice, such as seen here. When a potential is applied across the two ends of the crystal lattice, the ions tend to favor a certain direction. The anions which are negatively charged move towards the positive end, while the cations move towards the negative end. When no potential is applied across the ends of the crystal lattice, the ion motion is very random. This random motion does not conduct electricity. And this is how crystals conduct electricity due to the method of ion hopping. However, it is important to note that the conduction of electricity due to the motion of ions is much less than the conduction of electricity due to the motion of electrons. We will now go ahead to our next example. The amount of electricity conducted due to the motion of ions in a crystal is much less than the electricity conducted due to the motion of electrons. In this example, we will see how electrons conduct electricity in a crystal. Let us assume that these three atoms A, B and C are three atoms within a crystal lattice. Atom A has 7 electrons in its outermost shell. It has a hole to replace a spot covered by the 8th electron, while atom B and C have 8 electrons in their outermost shell. When a potential is applied across the two ends of the crystal, an electron from atom B moves to the spot associated with the hole in atom A, while the hole moves to atom B. Similarly, since the potential is still across the crystal, the electron from atom C moves to the place covered by the hole in atom B, while the hole moves to atom C. This motion of electrons constitutes an electric current. The current will be in the direction of the motion of the electrons. This is how electricity is conducted in crystals due to the motion of electrons.
Hi, I am Farza. I'm going to now explain about the magnetic properties of crystals with the help of arrows like this one, which represent magnetic domains. In solid state, metal ions of ferromagnetic substances are grouped together into small regions called domains. Thus, each domain acts as a tiny magnet. In an unmagnetized piece of a ferromagnetic substance, the domains are randomly oriented and their magnetic moments get cancelled. When the substance is placed in a magnetic field, all the domains get oriented in the direction of the magnetic field and a strong magnetic effect is produced. This ordering of domains persists even after the magnetic field is removed and a ferromagnetic substance becomes a permanent magnet. Substances like iron, cobalt, nickel, gadolinium and chromium dioxide are attracted very strongly by a magnetic field. Besides strong attractions, these can be permanently magnetized as explained. In the case of antiferromagnetism, substances like manganese oxide have domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other's magnetic moment. Hence, they would not possess any magnetism even after being subjected to a magnetic field. And in ferrimagnetism, it is observed that the magnetic moments of the domains in the substance are aligned in parallel and anti-parallel directions in unequal numbers. They are weakly attracted by magnetic field as compared to ferromagnetic substances. Magnetite and ferrites like magnesium ferrite and zinc ferrite are examples of such substances. These substances also lose ferrimagnetism on heating and become paramagnetic.
I'm going to talk about point defects, and in point defects I'm going to talk about vacancy defects. Vacancy defects is basically where an atom is not at its original place. So I'm gonna explain this by a model where an LED represents an atom. So you can see here that there is a grid which is lattice, and the atoms are missing from these particular lattice points, and because of this there's a vacancy created, which is called a vacancy defect, where the particular atoms, where you can see in this line, is missing from all these positions. It changes the properties of a particular atom or a group of atoms.
Hi guys, I'm gonna talk about interstitial defects, which comes under the point defects. In this type of defect, the atom occupies place outside the normal lattice position, and in this defect, the atom is of same type as of the lattice. Now we'll explain this model with the help of a LED. As we have seen, in interstitial defects, the atom occupies place other than the normal positions. For example, we can see here atoms here occupies the interstitial spaces, which indicates us the interstitial defect.
This one, I am going to explain about the planar defects. At first, what is a planar defect? A planar defect is a discontinuity of perfect crystal structure across a plane. I am going to explain about the different types of planar defects. The first type is grain boundaries. A grain boundary is a general planar defect that separates regions of different crystalline orientation within a polycrystalline solid. The atoms in a grain boundary will not be in a perfect crystalline arrangement. This region is known as a grain boundary. This was separated by the two grains. And coming to the second type, tilt boundaries. Between two slightly misaligned grains appear an array on these edge dislocations. This is known as tilt boundaries. The third type is twin boundaries. A twin boundary happens when a crystals on either side of a plane are mirror images of each other. Both are the two mirror images. This is known as the twin boundaries. Coming to the fourth type, microcracks. Microcracks occurs when internal broken bonds create new surfaces. They are about 10 micrometer in size, and there is a tendency to form a surface of a solid rather than in the bulk. These two bonds are broken. The size of the bonds are 10 micrometers.
Hi guys, I'm talking about linear defects. My objective and your objective is to understand what linear defect is. So there are two types of linear defects. One is edge, another one is screw. So talk about edge. You can see over here there's an extra line in the top half of the diagram. Well, these extra half planes insert in the crystal structure. So top half we have a thing called compression over here, and the bottom half we have tension. So this is a type of linear effect called as edge. And this diagram is called positive dislocation, and over this diagram is called negative dislocation. Well, let's go up again. So over here you can see in edge dislocation there's a line perpendicular, and we call this Burgers vector. And the dislocation motion leads to plastic deformation. So in this bottom half, I'm going to show you how the plastic deformation works, and with an example of Burgers vector. So over here, this is the negative side of a crystal structure. So over here you can see that the bottom half has an extra line over here. So how to alter this? So to alter this, let's erase this for now. Oh wait, not this. Give me a moment. Yeah. So I'm first taking this line, connecting over here as normal. This the line, because there's a stress applied over this side and a stress applied over here. The things shift towards one direction. So you can see there's a shift taking place. Naturally and slowly it takes place with an additional movement. Yeah, and that'll be extra. So yeah, basically edge location moves in the direction of the Burgers vector under shear stress. So what does all this lead to? Plastic deformation. The strength can be input by strain hardening and increased dislocation. Thank you.